Everyone, and welcome to the Chief Science Officer Zoom In on Science calls, where we learn about STEM professionals and their careers to understand the impact of their job in modern life. My name is Yusuf Fatma from Kenya, and I'm personally excited to host today's call. So for all of us to enjoy this experience, please mute your microphones and post your questions at any time during the presentation in the chat box. We'll be sure to have time after the presentation to answer as many as possible. Now, on past calls, we have learned a variety of different things, and today we welcome Mike Hudoba, who to Zoom In on Science, specifically coming to talk about DNA nanotechnology. So Mike, can you tell our participants a little bit about yourself and your work? Please share your slides, and remember, participants, post your questions in the chat.
Sure, thank you, Fatma. I'd be happy to. Let me get the sharing going on here. I was told you guys like a lot of pictures. So that was what I went for here. Yeah, so thank you so much for having me. It's an honor. It's one of my favorite parts about my job is sharing my passion for science and education with students, young and old, from kindergartners all the way up through the college level. So again, my name is Dr. Mike Hudoba. My students and most faculty just call me Dr. Mike because my name is slightly difficult to say. Even I mess it up sometimes, so it's okay. I am assistant professor in engineering at Origami University. It's a small university, about 3,000 students in Central Ohio. And actually just recently, I was promoted to the STEM Division Coordinator Liaison. So it's a really exciting opportunity for me to really work with all of our students, faculty, and the administration to really push for recruiting efforts, admission, getting the word out, social media, pretty much any and everything STEM. A little bit about me, as you can see, I was born, raised, went to school and work all in Ohio. So I was born and raised in a town called Canfield, Ohio, which is in the northeast of Ohio. And then when I graduated, I went to The Ohio State University in Columbus, which is in central Ohio. You might notice that I love Ohio. Ohio has my heart. I have had the opportunity to travel as much as I can. I've been all over the US, from Boston, Massachusetts, all the way to California and Hawaii. I actually was given the opportunity to study a little bit at the Technical University in Munich in Germany. And I did spend about a month traveling Eastern Asia and all around Australia. But Ohio has my heart. I love that Midwestern way of life. For those of you not in the States, for some reason, they call Ohio Midwest, even though it doesn't look like it's in the Midwest. But I went to school at Ohio State, like I said, for almost 12 full years. So I got my undergraduate degree in mechanical engineering. And after that, I started to fall in love with research and fabrication. So I continued on and got my master's work in user-centered product design, which I'll talk a little bit about. And then ultimately was given a great opportunity to start a brand new lab focusing on DNA nanotechnology, which again, we'll see it as part of my talk in the next couple of slides. I actually didn't even know that I wanted to become an educator until about midway through my PhD. I was a graduate teaching assistant, which basically is someone that helps the teachers with grading and teach smaller classes and run study sessions at Ohio State. And I absolutely fell in love with it. That actually got me involved developing science lessons for young students with a company called United Skates of America. So at different roller skating rinks, I created science lessons for field trips. And that's when I really found my passion. So during my last year of my PhD at Ohio State, I found the opportunity at Origami University. Origami was just starting their engineering program. We actually just finished our 5th year. So I joined up in 2016 when I finished my PhD as the 2nd faculty member, and have had the opportunity to do everything from build the curriculum to organize recruiting efforts to hire our new faculty. So it's been a really exciting opportunity. And you can see there in the top left, that's me in my Ohio State, we call it our wizard outfit when you get a PhD, but holding our Otterbein flambeau during the orientation session. And then just a little about me personally, 2 loves of my life are my 2 nieces there, my girls Emmeline and Drew. They just like Ohio, they have my heart as well. And then you'll see my buddies there. We are on a bowling team. I've been bowling for about 20 years. So that was after we won the championship match. So me and my two best buddies. Okay, so lots of pictures. So my job as someone in STEM, being in academia gives me opportunity to really combine three passions of mine. I work as an educator, I'm an engineer, and I'm also a scientist. And so I wanted to talk a little bit about all of these things and ultimately focus on some of my science work. But you know, as an educator, my favorite thing is the relationships that I can develop with my students. You can see in the top left there, two of our recent graduates who just graduated this past May. And one great thing about being an educator is I'm continuing to learn new stuff every day. In my science field, you know, I'm staying in DNA nanotechnology, I'm uncovering new things and I love it. But with teaching such a variety of classes and coming up with new projects, it really gives me opportunity to always improve myself and always improve my knowledge. We get to do some incredible projects. One thing I'm passionate about is our hands-on project-based learning. We never ever do the same project twice. You can see a couple pictures up there of different projects that from freshmen to seniors that we worked on in our engineering classes. The one that looks kind of like a spiral up there, you can see we actually worked with a company out of Costa Rica. They were inefficient in their way of drying coffee beans. They're a coffee growing company. And so what we were able to do with our students was work together and create an autonomous solar powered device that will actually spread and flip and rotate coffee beans. So just a lot of really unique projects that I think in a more traditional field, I wouldn't have the opportunity to kind of get my hands on. As an engineer, again, I'm continuing to grow as an engineer each and every day. Because of my work at Otterbein, I've actually fallen in love with automation, robotics, pneumatics, and hydraulics. So that first picture there, you can see developing different automated systems to maybe operate factory lines, things like that. That second picture there is I'm a video gamer. I'm proud of that. And so I kind of combine my love of user-centered design and gaming, and actually had created and fabricated a iPhone case that opens up to a fully functional video game controller. So you can play video games on your iPhone with tactile buttons. I'm always passionate, especially with my students, that engineers should be able to do more than just design. They should also be able to make. So that picture there in the center, my brother is a dentist, and we wanted to give one of his customers a trophy. So that was actually something I made from scratch, that toothbrush trophy. It's made out of wood. We call it the golden toothbrush. And I use a CAD-based software to actually model that on the computer, and then a really neat 3D wood cutting machine that allows me to kind of fabricate it, shape it, and present it in a really neat way. The other two pictures are different engineering projects I work with. The second from the right is a project I did with a veterinary surgeon who actually was developing a product that would help cure the incontinence of dogs. And so incontinence is when a dog, can't stop themselves from going to the bathroom. And this was the device, you can almost think of it like a balloon with no seams and no glue marks. And so it was a way to actually, that machine you're looking at there is called a gimbal. And it actually rotates about every single axis constantly. So it's constantly coating the outside of this mold. And so it creates a nice baggie without having any seams. So it was a really neat project for me to work on. And that final picture there is a picture of a robot that I worked on with one of my senior graduating students to graduate with honors and distinction. And we actually got to work with JP Morgan Chase. And that's a device that actually will automatically operate an ATM. And so you can slide that thing in front of an ATM and it can press the buttons and touch the screen and pull bills out and put checks in. It was a really neat opportunity for us to work with industry level folks. And then finally, as a scientist, so you can see I'm a bit of a wacky scientist, and I'm okay with that. So there's a couple crazy pictures down there, excuse me. But I do something called DNA origami. So a little bit about DNA and DNA origami. So for those of you that know DNA, when you think about it and you're shown pictures of it, right, you see this spiral pattern that we see in this first, or that third image there. And that spiral pattern is known as the double helix. It looks like you took a ladder and you spun the ladder up. Okay. And how DNA works is all of the rungs of the ladder, you can see the 4 different color rungs connecting that spiral pattern. We call those bases. Okay. And they have fancy names. There are 4 different bases: adenine, thymine, guanine, and cytosine. Knowing that isn't important. Even as scientists, we just call it A, T, C, and G. And what makes DNA origami possible, or what makes DNA possible, is that this DNA follows a certain set of rules. You can almost think of it like a puzzle. And in this puzzle, A and T are the only ones that fit together. And G and C are the only ones that fit together. And so when you have these 2 halves of a piece of DNA, if you line up the A's and the T's and the G's and the C's, the DNA will automatically form itself into this double helix shape. And when you think about DNA being in your body, right, that's the DNA that's in there. That's what's packed and wound tightly around something called a nucleosome, which is packed up into a supercoil, which ultimately is what makes up your chromosomes, which is what makes you, you, right? DNA is genetic, and that's what gives us all of our different attributes. But I don't use DNA that way, okay? I use DNA as a construction material. To me, DNA is nothing more than wood, cement blocks, bricks, right? Wire, anything that you might think to build a building or make a machine. That material, that's how I treat DNA. And I'll explain to you how we do this. So we basically have 2 major components with our DNA. And we have that scaffold there. You can see it's a really big, long loop of DNA. Okay, 1 big, long loop. And those bases I mentioned, A, T, C, and G, there's thousands of bases on this scaffold. And what we do is design what are called these staples. They're much, much smaller. You can see they're only about 30 to 50 bases. But we design them to be something called piecewise complementary to the scaffold. And so what does that mean? Well, complementary just means following those puzzle piece rules that I mentioned. Where there's a T, I put an A. Where there's a C, I put a G. Where there's a G, I put a C, right? And that makes it complementary. Piecewise means it's not complementary to 1 section. It's actually complementary to 2 sections that are far apart from one another. So if we look at this example that you see in front of us, imagine this being like a puzzle piece where the red part of the staple only could connect to the red part of the scaffold, and the green part of the staple could only connect to the green part of the scaffold. Same with the blue and the orange. If we put these 3 ingredients together in a tube and we heat them up and give them time, the only way for this puzzle to fit together is to kind of form this figure 8 type pattern. Okay, and so what that is that's 2 double helices that we treat as cylinders that are attached along their length. And that's just putting in 2 staples. What we do is we do this hundreds and hundreds of times to actually get the DNA to fold up and fold into complex machines that actually can move. They have dynamics to them, and we can do stuff with them. So there are a lot of different things we can do. I'll share one of my projects. You can see this was actually a force sensor, right? And so this force sensor, you can see it's a device made out of DNA. And the cartoon image there shows that it can actually be in 2 different stages. It can be totally closed or totally open, okay? And it can actually bounce back and forth in real time, bounce back from being closed to being open. The images on the far right are actually electron microscopy images. So these structures are actually, they're on the nanometer scale. So if you want to know how big a nanometer is, you can fit 1 million nanometers into a single millimeter. So slice up a millimeter into 1 million pieces, and that's a nanometer. And that's the scale that we're working on. And that's actually smaller than visible light. And so actually, we can't use a light microscope. We actually have to shoot it with a beam of electrons. Kind of like if you imagine putting your hand on the wall and your friends throw a bunch of paint balloons at your hand. What happens when you take your hand away? You see an outline of your hand. That's what you're looking at here with this device when you see these pictures. And what this does is actually measure forces. It's measuring the molecular crowding forces inside of a cell. the more crowded the inside of a cell is, the more it's going to be in its closed configuration. Imagine walking around, walking through a room with your friend and holding their hand. If there's no one else in that room, you can spread out, you can be far apart, you can come close together, right? You have a lot of room. But if you pack that same room in with a lot of people, you and your friend are going to be smushed together more often than you're going to be able to spread out far apart. And so what we can do is actually measure how much or how often it's in the closed configuration versus the open configuration. And we can actually use that to measure forces. And this device measures forces to 10 femtonewtons. And so if you want to know femtonewtons, it's kind of covered up there, but it's 0.000000022 pounds. I think I said the number of O's right. I can't see my screen, but it's very, very, very small. Very small amount of force that it can measure because it's measuring the interaction of cells and even what's going on inside of cells. So I thought I'd leave you with a little piece of advice here before we get to the questions. And my advice to you is to find a way to make your passion part of your career. At the top there, I've shown some of my passions. I absolutely love to play video games, and I still play old video games. You could see my setup there. I actually competitively play the video game Zelda, which I really love to play. I love to do puzzles, especially 3D puzzles. You might think that's a picture from my childhood, but that's a puzzle I made just last week. I love to cook. You could always find me in the kitchen. And again, there's me and my friends with our championship trophies. I love to bowl. And you might look at these activities and think, you know, how do they relate to DNA origami or science, right? Well, I'll end that by telling you a story. So I'm also a very big Ohio State Buckeyes fan. It's our college football team. You can see a picture of me there on the field. And the Buckeyes do this famous thing called the Script Ohio, where the marching band comes out and they write themselves. They follow a line and draw out the word Ohio. And it's called the Script Ohio. And I was giving a talk in Germany, and I put this slide up, and I showed this to kind of tell the students a little bit about myself. And they're not familiar with American football, but someone said, you should make that out of DNA. And it inspired me to start to develop this process. And I think, right, we designed this on a computer. The software that we use is kind of like a video game. So my video games help me learn this software, and the software helps me solve puzzles and think about things in video games. Same goes with puzzles. Being a scientist is no different than being a chef. You have to think about quantities and time. You have to be prepared. You have to experiment. Sometimes things work, sometimes things don't. And same goes with bowling. A lot of people think bowling, if you've ever been bowling, you just throw a round ball straight down a lane and hope you knock over some pins. But to me, bowling is all about geometry and dynamics. And that's what I had to think about when I thought about creating this Script Ohio. And so eventually, after about 3 years of work, I was able to use DNA and take a long strand of DNA and get it to fold into this shape. So you can see that big microscope there. That's an electron microscope. They're about $1 million. And I got it to fold into the Script Ohio shape. And I wasn't doing it for this reason, but after I created it, I found out that it was actually the smallest logo ever made with biological material. So I was contacted and eventually earned myself a Guinness World Record. So you can actually find Script Ohio has its own Guinness World Record. And so, yeah, so I will stop there and stop sharing my screen and be happy to answer any questions you might have.
Thank you very much for telling us about your work. It's evident you're truly passionate about DNA nanotechnology, engineering, and also being an educator, because I find that really amazing that you're all three. Now, while we're learning about what you do, participants have left questions in the chat. Let's start with a couple questions I had prepared. So firstly, who was your mentor as a child?
Yeah, it's a great question. And I've had a lot throughout the years, definitely some teachers of mine that, you know, whether it was, there's still a middle school teacher that I talk with once a month, still to this day. He was an inspiration to me and always encouraged me. But I definitely would say my father. So my dad was his own success story, and he's the one who really inspired my interest in science. One of my earliest memories, I remember him explaining to me the speed of light. And I mean, this is a memory from being very, very young, but I do remember sitting on his lap and we were at his desk and he was turning the lamp on his desk on and off, and getting me to realize that I don't have to wait. I don't see the light coming to my eyes. The light just gets to my eyes. It's instant, but it's actually not instant. It still has to get there. It just happens really, really fast. And that's just one of those earliest memories I have of really being awed and inspired and excited to learn more about science.
That's really sweet. I feel like, yeah, parents do play an important role in like shaping us for our future.
Absolutely.
So my second question is, what advice would you give to your 14-year-old self?
That's another great question. And I think, especially because I'm still figuring it out, it's absolutely 100% okay and normal not to know exactly what you want to do with your life. And you don't need to plan out every single step. You know, if you work hard, you follow your passions and you work hard, there's a good chance you're going to end up in a job that you love. I didn't know, for example, I actually didn't want to go to Ohio State because I thought it was too close to home, but it took growing up a little bit to realize that was the place for me, and I wouldn't have changed a thing. I remember the first thing I wanted to be was a neurosurgeon when I was young. I'm not sure why. I think just because it sounded cool. Then I wanted to be an architect. Then I wanted to be a design engineer. And it wasn't even until my PhD that I really found my passion for science and education. You know, when I started my PhD, I had no background in biology, but all of my previous interests kind of led me into this design. This DNA origami is designing and solving puzzles and creating and fabricating. So it was really neat to really just kind of let my life unfold. You know, keep your eyes open, but don't think you have to have everything laid out because things will change.
Yeah, that's really inspiring. And I feel like a lot of kids these days really need to hear that, because some of them like feel pressured and like tensed because they have a feeling that they need to like have it all planned out, so like they don't disappoint their parents or they don't disappoint themselves.
No, if you, like I said, the first line there, work hard and follow your passions. I mean, you will end up doing something that you love. And if you love what you're doing, chances are you're going to be successful at it. So like I said, it took me, 24 years to even think about being an educator. And now I look back, I couldn't imagine being anywhere else.
Okay, thank you very much. Now let's move on to the participant questions. So our first question is from CSO Haley from Oregon. And she asks, what is your favorite branch of science? For example, biology, chemistry, or physics?
Oh, great question. So I know this is not part of one of your examples, but I always say, I would say math and physics, because math is the language of physics. And then I always say engineering is the application of physics. My physicist friends would yell at me, but if I was picking there, I would say physics. You know, to me, physics is just an understanding of the way the world works, why things happen, and understanding the unknown, and whether it's theoretical or experimental. Really being able to look at something and say, okay, I know that that's happening, but why is that happening? What is the cause of that? What is the cause and effect? What is the principle behind it? And the fact that, you know, physics and our understanding and the use of math within physics is just universal. You know, if we were on another planet in another galaxy, we would have different words for numbers, but math would still be math. They would still know about the value of pi. They probably wouldn't call it pi, and it wouldn't be 3.141, but it would mean the exact same thing because it's a constant. And our understanding of physics there would be 100% the same. That being said, I did get into the biology game late, like I said, not until my PhD, and I've truly become fascinated by biology and just life and how life works and how life evolves. And so I'd love to be able to say all three, but if you force me to pick, I would say physics.
Well, physics can be fun. It's just you have to know what you're doing, and then
Yeah.
that's the only way, like, you know, that's how it becomes fun.
Oh, absolutely. And it's all about trial and error. Don't be afraid to fail. You know, physics is even just from a class standpoint, is a really challenging subject. And that sometimes discourages some students, but hopefully for those willing to work hard, it inspires you. You know, you learn a lot from failure, and just that sheer desire to understand, I think, is what makes a good scientist a good scientist.
Yeah, totally. Okay, so our second question is from Kelly from CSO International, and she asks, how long does it take to create the scaffold into a new picture, and what is the reason behind this work? What is the end goal?
Great question. So to do the design of a structure, it can take, if it's a simple design, I've obviously been doing it for years, I can do it in a day. A complex design, you know, I didn't devote my full life to it, but the design for that Script Ohio took about 2 years. So you can see it varies depending on the complexity of the structure. And then once you have the design, it takes about a week to fabricate it. So you can go from just a collection of all these individual pieces of DNA, and then when you mix them all together and actually create the machine, that takes about a week. I will say one exciting thing that we're doing, so that nanodyne, that force sensor you guys saw, that was some of my previous work. But work that I'm currently researching is actually, what we've done is found a way to actually do this DNA origami fabrication and analysis in 60 total minutes. And we've designed procedures and protocols that we're going to be providing to middle school and high school students. And so middle school and high school educators and their students can actually, with very basic equipment, nothing more than a thermometer and a Bunsen burner or a hot plate, you can actually make these in about an hour. So it's really fascinating what we're trying to do. What is the reason behind this work and end goal? I'm gonna give you 2 answers to that question. So some of the things that we have done, and when I say we, I mean the field, not me personally, but people in my lab or other people in the field, my device was to measure forces. There are a lot of devices that are going into drug delivery. So for those of you that are familiar with different cancer therapeutic drugs, one of the negative aspects of cancer therapeutics is that they kill all of the cells as opposed to just the cancerous cells. And so we're using DNA origami, creating almost a little capsule that actually will only target the cells that it needs to kill. And so it's a way to keep healthy cells away from these cancerous drugs. DNA origami isn't being used to create new drugs, it's being used to deliver them in a more efficient way. Another very new area that is really fascinating to me is digital data storage. So for those of you that know a bit about computers, right? Everything in a computer, even my image being transmitted to you guys right now, is a collection of ones and zeros in a different sequence. Well, what did I say DNA is? A sequence of A's, T's, G's, and C's. DNA is nothing more than information carrying, okay? And so I like to tell this, if you took all of the digital information that exists on planet Earth, it's about a zettabyte, which is 10 to the 21st. So take a 10 and put a bunch of zeros after it. That's how bytes, that's how much digital information exists in the world today. If we took all of that, converted it into DNA, and put it to its theoretical maximum size, all of it would be about the size of a sugar cube. You would be able to sit it on your desk. It wouldn't need power and it wouldn't need heat or cooling, and it would last for 500 years. So it's a very interesting path forward in terms of this research. Because the other, what is the end goal? That's one of my favorite things about science is I don't know, I don't begin to know, right? What I like to do is I take a piece, I contribute my work. And how science works is one of you guys comes along in a couple years and you grab that work and you do something new with it. I always like to tell the story. Einstein wrote a paper on the behavior of light. And ultimately what he learned from this paper is something called light amplification through stimulated emission of radiation. So I'll say that again, light amplification through stimulated emission of radiation. If you write that out and look at the first letters of those words, it spells laser. That is what a laser is. Einstein did not study light with the intention of, I'm gonna make lasers that can use on PowerPoints and create hard drives and create medical equipment. He didn't know that. He was just curious about how light works. Somebody else later on said, ooh, I can do something neat with this. And he would have never dreamed that he was the reason we have hard drives and computers.
Oh, wow. It's very interesting. So our next question is from Cecil Tristan from Arizona. He asks, have you ever used reactive ion etching to modify or engrave biological materials or electron beam lithography? I'm not sure if I pronounced that right.
Yeah, lithography. Yeah, so great question. That is actually not something I've ever personally done. I know, and it's funny you mentioned this, I have an undergraduate engineering course. So lithography, you can almost think of it as, you know, pasting down a picture almost, so to speak, to explain it. And so in one of my undergraduate courses, I have students develop their own research project, and it has to use DNA in some way. And actually a recent student actually did the research and laid out a project to actually combine lithography to engrave with the addition of DNA origami. So I haven't yet, but a student of mine very recently may have inspired me to give it a try.
Thank you so much for your participation today, Dr. Mike. Before we close this call, we have one final question. What advice would you give to us as young leaders for the future?
Sure. You know, I always like to just, I don't like to read recorded scripts when I give talks like these, but you did send me this question in advance. And actually, my second year at Otterbein, I was actually given the award for New Teacher of the Year. And one of the things that came with that is I got to give the address to the next year's incoming class. And there's a section of that I really think fits this question well. And so I thought I'd just share that with you. So I think the advice is ultimately to recognize the difference between knowledge and intelligence. Many people incorrectly think that knowledge and intelligence are the same thing. Not only are they vastly different, but they are also not mutually inclusive. A computer has an infinite amount of knowledge, but when it comes to intelligence, it's dumb as a box of rocks. Books and the internet are a collection of pretty much every piece of knowledge on the planet. If you have access to internet and to books, you are as knowledgeable as anybody else in the world throughout all of human history. But that is why intelligence is so important, because knowledge is useless if you don't know what to do with it. Intelligence is analyzing information and understanding what to do with that information to solve a problem. At Otterbein, I teach a course on dynamics. One day, actually 2 semesters ago, we were doing a problem in class where we had a block attached to a string or attached to a rod by a string, and the rod was rotating. And the students were asked to calculate the radial component of the angular momentum of the block. And I overheard a student mutter, "When am I ever going to know how to do this in my career?" And I wasn't afraid. I stopped the class, I looked him right in the face, and I answered honestly, "Never. You will most likely never have to calculate the angular momentum of this block attached to this rotating rod." But that is not what I was teaching them. I was teaching them how to take information they know and how to be able to solve a problem. And so I'll just end you guys there.
Again, we thank you so much for joining us today, Dr. Mike. You're an inspiration to many of us, and we hope that you can participate in another call someday as we continue to zoom in on science. CSOs, to close the call, please join me in saying our motto. CSOs, don't just hope it happens.
Make it happen.
Thank you all so much for joining us today. I hope you all have an amazing day ahead of you, or a good night's sleep, wherever you are in the world. This has been amazing, and I will see you all next time. Thank you.
Thank you guys so much.
Great job, Fatma.
Really
Wait,
great
you were so
talking.
great. No need to be nervous. And thank you, Mike. That was awesome.
My pleasure. No, this was happening. Yes, a very good job. You're like a pro. It sounds like you've done this 100 times.
Thank you, everybody, for joining the call. And Mike, I'll send you the video soon. Thank you.
Awesome. Thank you again.
Bye, guys.
Bye.